Welcome back to Quantum X. In today's video, the project takes us deep into a Japanese forest, where a traditional wooden house is being built using classical craftsmanship. No heavy machinery, no modern concrete systems, only natural timber, precise joinery, and construction knowledge refined over generations. This video documents more than the build itself. It examines how Japanese builders approach structure, material selection, and forest conditions to create a durable, self-sustaining home. Let's break down each construction stage through the lens of real-world building practice. The project begins with clearing the forest site, a phase that directly influences the long-term stability of the structure. The team removes fallen leaves and surface vegetation to expose undisturbed soil, allowing a proper assessment of soil density, moisture content, and natural bearing capacity. Large logs are relocated away from the site. In a damp forest environment, temporary heavy loads can cause localized settlement and distort ground levels from the outset. Tree stumps are completely excavated. Any remaining root systems will decay over time, creating underground voids that lead to uneven settlement beneath timber foundations. After clearing the site, the next phase focuses on leveling the building area and establishing construction access. The ground here consists mainly of clay soil, which retains water and quickly turns muddy under rainfall. Left untreated, access roads would deform under vehicle and material loads. Instead of using concrete, the team spreads crushed stone to form the road base and temporary parking area. This gravel layer creates passive drainage, allowing rainwater to percolate downward rather than pooling on the surface. Crushed stone also distributes loads more evenly, reducing localized settlement caused by repeated movement of trucks and timber. Leveling is done with restraint, adjusting elevations only where necessary. This preserves surrounding soil structure and maintains the natural balance of the forest terrain. This stage provides critical site infrastructure, ensuring stable and reliable construction access throughout the build, even in wet conditions. At this stage, crushed stone is spread to a thickness of 10 to 20 centimeters, depending on the weakness of the underlying soil. This depth is sufficient to distribute loads effectively while acting as an active drainage layer across the site. Once placed, the gravel is compacted using a vibratory plate compactor. Compaction forces the stones to interlock, reducing voids and minimizing post-construction settlement. Skipping this process would lead to shifting surfaces under dynamic loads from vehicles and equipment. Along the edges of the gravel base, large timber logs are installed as retaining elements. Their mass provides stability, while the porous interface allows water to pass through naturally, unlike impermeable concrete walls. This method prevents gravel migration during heavy rain and aligns with traditional Japanese building principles that prioritize simplicity and the use of on-site materials. The next phase involves excavating trenches for the water supply system, an underground component critical to long-term functionality. In this region, the seasonal frost depth reaches approximately 70 centimeters. Any pipe installed above this level risks freezing, leading to cracks, leaks, and service failure during winter. To prevent this, the entire water line is placed at a minimum depth of 70 centimeters, safely below the frost line. The construction team excavates a continuous trench extending nearly 50 meters, running from the water source through the forest to the building site. Excavation is carried out carefully to avoid unnecessary disturbance to surrounding soil, while maintaining a controlled gradient for drainage and future maintenance access. This reflects a standard off-grid construction strategy in cold climates, address environmental risks at the infrastructure stage long before the structure above ground is completed. Once trenching is complete, the next step is joining the water pipes, a phase that demands high precision since the system will be permanently buried. Instead of using conventional mechanical fittings, the team applies thermal fusion welding to connect the pipes. This method works by heating the ends of two pipe sections to a controlled melting temperature. Once softened, the surfaces are pressed together and held in place until fully tooled. The result is a single continuous material with no physical seam between the pipes. This eliminates leakage risks associated with aging rubber seals or thermal contraction. In cold, moisture-rich forest environments where pipes experience seasonal temperature fluctuations, thermal fusion provides superior strength and watertight integrity. It is the preferred solution for underground water systems where future access and repairs would be both difficult and costly.
Once the pipeline installation is complete, the team proceeds with water pressure testing, the final step to verify system integrity and safety. During the initial test, a minor leak appears at one joint, where adhesive had not fully cured. During the second test, the system successfully withstands a pressure of 1.75 megapascals for 1 full minute without any leakage. The pressure is then released and stabilized at 1 megapascal, maintained continuously for 1 hour. In standard practice, maintaining 0.8 megapascals is already considered a successful test.
After the water system passes inspection, the team proceeds with installing electrical wiring and UTP internet cables. All cables are routed together inside a single protective conduit, simplifying routing control and reducing the number of trenches required in the forest. This utility conduit is buried along the same route and depth as the water pipeline, forming a unified underground infrastructure corridor from the supply point to the building. Housing the cables inside a conduit protects them from moisture, insects, and mechanical damage, while allowing future replacement or upgrades without re-excavation. In off-grid environments with complex terrain and weather conditions, this approach minimizes risks caused by soil movement or surface freezing. Careful spacing and insulation ensure electromagnetic safety and long-term reliability. It is a practical, low-maintenance solution commonly applied in remote timber construction projects.
With all underground utilities completed, the project moves into a critical phase, excavating foundation pits and trenches for the timber structure. Excavation is carried out using a combination of manual work and light machinery, ensuring design depths are met without disturbing surrounding soil stability. Before foundation work begins, each pier location is carefully measured and aligned to the building grid. Even minor inaccuracies at this stage can result in misalignment of the timber frame later on. Wooden stakes reinforced with packed stones are used to mark pier positions. This simple method provides stability and prevents displacement during excavation and material handling. The stone packing keeps the markers upright while clearly indicating center points and elevations on an uneven site. This approach reflects traditional construction logic, achieving precise geometry at the foundation stage because the entire wooden superstructure depends on these initial reference points.
Once excavation is complete, the entire foundation area is covered with a layer of crushed stone to form a stable base and isolate the structure from underlying moisture. This layer helps distribute loads evenly while reducing capillary moisture rising toward the timber foundation elements. Next, the team constructs the foundation frame using wooden stakes and boards, clearly defining the footprint and boundaries of the foundation. This step is critical for geometric and elevation control. Laser leveling tools are used in combination with water columns to establish precise foundation height. Lasers provide fast, accurate reference across the site, while water columns verify levels in areas with limited visibility. After layout confirmation, the entire crushed stone surface is compacted using a mechanical plate compactor. Compaction reduces voids, locks the aggregate in place, and minimizes future settlement. This stage finalizes the foundation base, directly influencing the long-term stability of the wooden structure above.
With the foundation base fully prepared, the project moves into pouring the perimeter concrete footing around the floor structure. Concrete is supplied by a ready-mix truck, ensuring consistent mix quality and controlled proportions throughout the footing. Rather than pouring directly, the concrete is discharged into a metal hopper equipped with a bottom release gate. This allows precise flow control, minimizing segregation and material loss. An excavator lifts and positions the hopper, placing concrete accurately along the foundation perimeter. This method is especially effective in confined forest sites, where direct truck access is limited. During placement, a mechanical vibrator is used to remove trapped air and ensure the concrete fully consolidates within the formwork.
Proper vibration improves concrete strength, eliminates honeycombing, and ensures the footing can reliably support the timber structure above. After the perimeter concrete has set to initial stability, the team establishes reference lines for all subsequent construction stages. A continuous straight line is snapped around the foundation using a chalk line reel. Next, the exact foundation layout is re-established using laser equipment. Laser alignment transfers design axes from drawings to the site with high precision, especially valuable on uneven ground. This reference controls straightness, squareness, and alignment of the timber structure to follow. Compared to point-by-point measurement, a chalk line allows rapid visual detection of geometric deviations along the entire foundation perimeter. Once the foundation layout has been precisely established, reinforcement steel is delivered to the site for fabrication and installation. The process begins with measuring and marking each steel bar according to the structural drawings. Accuracy at this stage is critical, as even small deviations can affect concrete cover and load distribution within the foundation. The bars are then cut and manually bent using simple leverage tools and fixed anchor points. While basic, this manual technique allows craftsmen to control the exact bending angle of each bar. It is particularly practical for remote forest construction sites where heavy machinery is difficult to bring in. After shaping, the steel bars are assembled into reinforcement cages according to the structural design. These cages act as the tensile component inside the concrete, while the concrete itself mainly resists compression. Together, they form reinforced concrete, a composite system capable of handling structural loads while controlling cracking. This hidden reinforcement framework becomes the structural skeleton of the foundation supporting the timber house above. After the primary reinforcement frame is prepared, the crew begins securing metal hardware into the sub-slab concrete to establish the formwork system for the foundation slab. These metal fittings act as anchor points, holding the formwork firmly in place when concrete is poured. In foundation work, formwork rigidity is essential, because the pressure of fresh concrete can deform poorly secured molds. Next, reinforcement bars are placed on the ground in a square grid pattern, forming a distributed reinforcement layer across the entire slab area. Uniform spacing between the bars ensures that concrete can fully encapsulate the steel, creating a strong mechanical bond. To maintain the proper concrete cover, small granite stones are positioned beneath the reinforcement grid. These spacers lift the steel slightly above the base surface so it remains centered within the future concrete layer. This small detail plays a major structural role. If reinforcement sits directly on the ground, corrosion protection decreases, and the structural performance of the foundation can be significantly compromised. Before assembling the formwork, the crew applies a special release oil to the surface of the steel panels. This coating acts as a separation layer, preventing hardened concrete from bonding tightly to the metal surface. After preparation, steel formwork panels are assembled around the foundation area. Compared with wooden forms, steel panels provide greater rigidity, resist deformation, and produce a more precise concrete surface. Between the steel panels, the team installs plastic spacer blocks. These small components control the spacing between the formwork and the reinforcement, ensuring the concrete cover thickness meets the structural design. A row of horizontal steel pipes is installed behind the formwork panels, tying the panels together into a unified structural frame. These connectors help maintain straight alignment and prevent the panels from bulging outward during the concrete pour. In addition to the horizontal connectors, several inclined steel braces are installed from the formwork down to the ground. These braces act as structural supports, transferring loads into the soil and stabilizing the entire formwork system. With this reinforcement in place, the formwork can maintain its designed shape throughout the pouring and curing stages of the concrete foundation. In concrete construction, the lateral pressure of fresh concrete can be significant, especially during continuous pours. Without sufficient reinforcement, the formwork could shift or deform, leading to inaccurate foundation dimensions.
With everything prepared, the concrete pouring phase begins. This time, the crew uses a concrete pump truck, allowing the material to be delivered quickly and accurately into the foundation area. Concrete is mixed inside the mixer truck and then transferred into the pump hopper, where it is pushed through pipelines to the placement location. As fresh concrete flows into the formwork, it generates significant lateral pressure against the steel molds. During the pour, some of the steel reinforcement pipes behind the formwork begin to shift slightly, revealing just how strong the pressure from wet concrete can be. Once the concrete reaches the required elevation, the surface is leveled using a screed bar to create an even slab surface. At the same time, concrete vibrators are used to remove trapped air and ensure the material fully surrounds the reinforcement. Proper vibration increases concrete density, reduces honeycombing, and ensures the foundation achieves the structural strength needed to support the timber structure above.
After about 1 week of curing, the concrete foundation has gained enough strength for the formwork to be removed. Once the concrete stabilizes and reaches its initial structural hardness, the construction crew begins dismantling the steel formwork system. Bolts, braces, and metal connectors that hold the form panels together are carefully loosened and removed. Because a release oil was applied to the steel molds before the concrete pour, the panels can be separated from the hardened concrete without damaging the surface. Each steel form panel is gradually lifted away, revealing the solid concrete foundation underneath. As the formwork comes off, the true shape of the foundation becomes visible. The edges appear straight and well-defined, while the concrete surface looks dense and uniform, an indication that the pouring and vibration processes were done correctly. In the end, a complete foundation measuring 4.5 meters by 11.8 meters stands finished. This structure now serves as a strong and stable base for the upcoming construction of the timber house above. With the concrete foundation completed, the next step is preparing the wooden materials used to build the house walls. Lumber pieces sized 2x4, along with plywood sheets, are delivered to the construction site and begin to be processed according to the dimensions specified in the design plans. Each wooden piece is first carefully measured and cut to form the structural parts of the wall frame, including the bottom plate, top plate, and vertical studs. These pieces are then arranged on a flat surface and nailed together to create complete wooden wall frames. Assembling the wall frames directly on top of the concrete foundation helps ensure accurate dimensions and proper alignment with the building layout. 90mm nails are loaded into a pneumatic nail gun to speed up construction. The nail gun is connected to an air compressor through a hose, ensuring consistent pressure so that every joint is firmly secured. The wooden studs are positioned according to the construction layout and quickly fastened together using the nail gun. During this process, openings for doors and windows are intentionally left within the wall frames based on the design specifications. The top section of each window opening is reinforced using 2x6 lumber, forming a header beam that helps distribute structural loads from the wall above to the sides of the frame. This prevents the window frame from carrying excessive weight from the upper structure. Throughout the assembly process, builders also pay close attention to the natural twisting and warping of lumber, carefully positioning each piece to minimize deformation and maintain straight, stable wall frames. Plywood panels are also attached to reinforce the frames, increasing the rigidity and stability of the entire wall structure. This method allows large sections of the wall to be prepared in advance, making the later stage of raising and installing the house frame faster and more efficient. Each panel is carefully aligned and placed against the studs so the fasteners distribute loads evenly across the frame. At door and window openings, the panels are precisely marked and cut to match the pre-framed openings.
Accurate cutting ensures that the structural integrity of the panel is maintained, while allowing proper clearance for future window and door installation. For this stage, the crew switches to 50mm nails instead of the 90mm nails used during framing. The shorter nails are better suited for fastening sheathing panels to the studs without penetrating too deeply through the lumber. At the same time, the pressure of the pneumatic nail gun is reduced to match the nail size. This adjustment ensures the nail heads sit flush with the panel surface without cracking or damaging the wood. Once installed, the sheathing panels function as a structural bracing layer, preventing the wall frames from twisting and significantly improving the overall stability of the timber house structure. With the timber wall frames prepared, the next step is establishing the connection between the wooden structure and the concrete foundation, a technique strongly influenced by traditional Japanese carpentry principles. Large square timber beams are carefully prepared by carving both round and square holes at specific connection points. These openings allow precise alignment with the steel anchor bolts that were previously embedded in the concrete foundation. Before installation, the timber surfaces are coated with a protective oil finish, which helps reduce moisture absorption and improves long-term durability. A foundation gasket layer is then placed between the timber beam and the concrete surface. This layer serves several important functions. It allows air circulation beneath the floor, helps prevent termite intrusion, and acts as a barrier to stop moisture from wicking upward into the wood. Next, the base beams are positioned directly over the pre-installed steel anchor bolts embedded in the foundation. Once the bolts are tightened, the combination of timber joinery and steel fasteners creates a highly secure structural connection. This connection ensures that the entire load of the timber house is safely transferred into the concrete foundation, forming a stable base for the structure above.
Once the base beams are firmly secured to the concrete foundation, the crew begins raising the prefabricated timber wall frames. Because of their large size and considerable weight, some wall sections are intentionally left without sheathing panels to reduce weight, making them easier to lift and maneuver. Typically, at least 4 workers are required to coordinate the lifting and positioning of each wall frame onto the foundation beam system. The frames are rotated upright and aligned carefully with the layout lines previously marked on the foundation. Once the wall frame is positioned correctly, structural nails are driven to secure the frame to the base beam while also connecting adjacent wall sections together. If you found this video interesting or helpful, feel free to leave a comment below. And if you have any professional insights, practical experience, or a different perspective related to what you saw in this video, we'd love to hear from you. Your comments can help provide more knowledge and real-world viewpoints for everyone watching. We truly appreciate any contribution you're willing to share with the community. And if you'd like to support the channel, the simplest way is to hit the like button, share this video with others who might find it useful, and subscribe to the channel so you don't miss our upcoming videos. Your support really helps us continue creating more valuable content in the future. After the primary wall panels are in place, additional 2x4 lumber members are installed horizontally across the top of the wall frames. These pieces function as top plates, tying the individual wall sections into a unified structural system. This locking mechanism significantly improves structural stability, preventing movement and preparing the frame for the next stages of construction above. With the wall framing stabilized, the construction team begins preparing large square timber beams to fabricate the roof truss system, the primary load-bearing structure of the roof. Connection points on the beams are precisely drilled, cut, and carved using a combination of power tools and hand tools. The goal is to create traditional mortise and tenon-style timber joints, allowing the beams to interlock tightly without relying entirely on metal fasteners. These joints are a hallmark of Japanese carpentry techniques. When crafted correctly, they create extremely strong connections while allowing the wooden structure to naturally distribute loads and accommodate slight expansion or contraction caused by changes in temperature and humidity. Diagonal holes are drilled through the intersecting timber members, allowing structural screws and steel bolts to tighten the connection securely. This diagonal drilling technique distributes the clamping force across multiple surfaces while reducing the risk of joint slippage or twisting when the roof structure is under load. Combining traditional mortise and tenon joinery with modern metal fasteners creates a hybrid connection system that offers both strength and flexibility, an approach commonly seen in modern timber construction, inspired by Japanese carpentry. After the joints are secured, The carpenters use a crowbar to create small indentations on the timber surface. These marks contribute to a handcrafted aesthetic and can also help finishing materials adhere better. Next, a hand grinder is used to smooth and round off sharp edges. This step removes splinters and prepares the timber surface for the next stage, applying a protective coating that will preserve the wood over time. After machining, the beams are coated with a brown protective finish. This treatment helps protect the timber from moisture, ultraviolet exposure, and long-term weathering. Finally, the prepared beams are assembled into large roof truss frames. These trusses will act as the main structural skeleton of the roof, transferring the roof loads down into the timber wall system below.
Once all timber components are prepared, the roof truss frames are assembled into large sections ready for installation. Because of their size and weight, the construction crew uses a simple but effective lifting method. Ropes are tied to nearby trees surrounding the site, forming a basic manual hoisting system. By using multiple workers pulling the ropes and leveraging the natural anchor points, each truss frame is gradually lifted and guided into position at the top of the wall structure. After the trusses are aligned correctly, a long purlin beam is installed along the roof line. This beam connects 3 truss frames together, effectively locking them into a single structural unit. The purlin helps distribute roof loads more evenly and improves the overall stability of the roof frame. In the final step of this stage, prefabricated timber roof panels are installed on top. The underside of these panels has already been covered with thin wooden boards, which serve as an interior sealing surface while also adding stiffness to the roof structure.
Once the roof framing has been fully stabilized, the next step is roof insulation. The roof beams are intentionally spaced according to calculated intervals, creating standardized cavities between members. This spacing is designed to match insulation dimensions, allowing faster installation and improving thermal performance. In this project, the crew installs fiberglass insulation between the timber members. Fiberglass traps small pockets of air within its fibers, significantly reducing heat transfer through the roof structure. After the insulation is placed, the entire roof surface is covered with plywood sheathing. This sheathing forms a rigid and continuous base that distributes loads from the roofing materials above and strengthens the roof structure. Next, a waterproof membrane is installed. Its purpose is to prevent rainwater or moisture from penetrating into the timber structure beneath. The final exterior layer will be roof tiles, which lock the entire roofing system together and provide long-term weather protection. However, this final roofing stage was completed later and is not shown in the video. Once the main house structure is established, the crew moves on to building the deck foundation for the porch area, an essential open space in traditional timber houses. The process begins with digging pier holes at locations previously marked according to the structural layout. These holes will serve as the load-bearing points for the entire porch deck structure. After excavation, crushed stone is placed at the bottom of each hole to create a drainage layer and stabilize the soil. The stone base is then compacted using a vibrating compactor, increasing material density and reducing the risk of future settlement. Next, precast concrete pier posts are carefully placed into the prepared holes. These elements are typically manufactured with standardized dimensions and strength ratings, allowing faster installation compared to casting concrete directly on site. These concrete piers act as primary load transfer points, carrying the weight of the porch beams and deck structure safely down into the stable ground below. Once the concrete piers are firmly positioned and stabilized in the foundation holes, the crew begins installing the load-bearing timber posts on top of them. These posts are typically secured using steel brackets or anchor bolts, which prevent direct wood-to-concrete contact and reduce long-term moisture damage. These vertical posts act as the primary support columns for the porch deck, transferring loads from the beams and floor structure down into the concrete piers below. Next, horizontal timber beams are installed and fastened together with structural screws to create the deck joist system. The joists form a structural grid that distributes loads evenly across multiple support points. The spacing between joists is carefully calculated to prevent floor deflection when weight is applied. Once completed, this framing network becomes the structural base of the porch deck, ready to support the installation of decking boards in the next construction phase. With the porch posts and deck frames securely installed, the crew proceeds to install another joist system above to support the porch roof structure. This joist system functions similarly to the main roof framing, distributing roof loads down through the timber posts and into the concrete piers below. Once the porch roof frame is completed, the insulation and roofing process follows a method similar to the main roof, previously shown.
Below, attention turns to the deck structure. The joist beams are first coated with a protective sealant. This treatment helps resist moisture, slows down wood decay, and significantly extends the lifespan of the structure, especially since porch decks are exposed to outdoor conditions.
Deck boards are installed on top of the joist system below, forming the finished porch floor, an open transitional space connecting the house to the surrounding forest environment. With the wall framing and main structural elements already in place, the construction team begins installing the interior floor system. The process starts with metal support brackets being fixed to the base wall beams, creating strong anchor points that connect the floor system to the house's structural frame. Next, adjustable screw posts are attached to the wooden floor beams. To strengthen the connection between metal components and the concrete foundation, a specialized bonding adhesive is applied between the steel plates and the concrete surface. At the same time, the base plates of the joist supports are nailed securely into the concrete, locking the floor structure firmly in place. Once the floor frame is fully aligned and secured, the structure is ready for the installation of the final floorboards in the next stage of construction. These threaded supports allow the builders to fine-tune the height of the floor structure, ensuring the entire surface is perfectly level before the finished flooring is installed. Before installing the finished floor above, the construction team proceeds with insulating the foundation and preparing the building's utility systems. The process begins with measuring and cutting polystyrene foam boards to match the dimensions of the foundation areas. This material provides excellent thermal insulation, helping reduce heat transfer between the house interior and the outside environment. Before the insulation boards are installed, electrical wiring and water supply lines are routed through the foundation area. These lines are carefully connected to the underground pipes that were installed earlier during the foundation excavation stage, ensuring the building's infrastructure is fully integrated from the ground up. Once the wiring and plumbing lines are secured in place, a specialized construction adhesive is applied to the surface of the foundation. The polystyrene foam panels are then pressed firmly onto the concrete, creating a continuous insulating layer. This insulation not only improves the thermal performance of the house, but also helps protect the foundation structure from temperature fluctuations and moisture over time. The spaces between the foundation wall and the insulation panels are filled with expanding urethane foam. This material effectively seals small cavities, preventing heat loss while blocking cold air and moisture from entering the structure. At the same time, the wastewater plumbing system beneath the floor is finalized, connecting the pipes to the drainage lines that were installed earlier during the foundation construction phase. Completing these utilities at this stage ensures that all plumbing components are properly positioned and inspected before the floor structure is closed. With the insulation and plumbing systems completed, the crew proceeds to install the secondary floor joists. These joists are laid perpendicular to the primary floor beams and connected to the adjustable screw supports that were previously installed, helping distribute loads evenly while maintaining a stable floor structure. Finally, plywood sheathing panels are installed across the entire floor frame, covering the structure and forming a solid base for the interior flooring layers that will be added in the next stages of construction.
Once the main floor structure of the house is completed, the crew begins working on the loft level, a mezzanine space designed to increase the usable interior area without significantly raising the overall height of the building. The timber beams for the loft floor are first cut according to the design dimensions. At the ends of the beams, precise joinery cuts are made, allowing the beams to fit securely into the wall structure or onto the prepared support points. After the joinery work is finished, the edges and corners of the beams are carefully sanded to remove splinters and create a smooth surface, which also helps protective finishes adhere better. At the same time, steel brackets used to support the loft beams are fabricated. Steel plates are bent into the required shapes, then sanded to clean and smooth the metal surfaces before receiving a black protective coating that helps prevent corrosion.
With the timber beams and steel brackets prepared earlier, the crew proceeds to install the loft structure inside the house. First, a large timber beam is positioned parallel to the central roof truss, serving as the primary support beam for the loft floor. This beam is supported by the custom-made steel brackets fabricated earlier, which are securely fastened directly to the central truss to ensure structural stability. From this main beam, loft floor joists are installed spanning toward the wall. On the opposite side, another horizontal beam has already been anchored to the wall framing, providing a second support point for the floor system. Once the primary joists are in place, secondary support members are installed across the frame to further strengthen the structure and distribute loads more evenly across the loft floor. Finally, plywood panels are laid across the entire loft surface and secured with nails to lock the structure together. With the decking complete, the loft platform becomes a practical storage space, efficiently utilizing the upper interior volume of the house while keeping the main living area below open and uncluttered. Insulation materials are placed into the cavities between the timber wall studs, helping reduce heat loss and maintain a more stable indoor temperature despite outdoor weather changes. At the same time, electrical outlets and wall-mounted electrical boxes are installed within the framing. These components must be positioned before the wall surfaces are closed so that wiring can be neatly routed inside the structure. Next, the crew constructs the wall framing for the bathroom area. This wall is carefully positioned to align with the drainage pipes that were installed earlier during the foundation stage, allowing the plumbing system to connect efficiently and accurately. Finally, plywood panels are installed over the wall frames, enclosing the structure and forming a solid base layer. This sheathing prepares the walls for the next stages of interior finishing, such as decorative panels, drywall, paint, or other surface materials that will define the final appearance of the living space. In the final stages of construction, the team installs the steel-framed glass windows and doors. These elements not only complete the architectural appearance of the house, but also allow natural light to fill the interior spaces. Each window and door frame is carefully placed into the openings that were prepared earlier in the timber wall structure. After aligning the frames to the correct level and position, the crew secures them to the wall framing and seals the gaps to ensure proper insulation and weather resistance. With the glass openings installed, the house finally becomes an enclosed structure, ready for the interior finishing phase. Looking back at the entire construction journey, from foundation excavation, plumbing installation, timber framing, and roof truss assembly, to floor and wall construction, every stage required precision, teamwork, and practical building experience. If you found this video interesting or learned something new about the process of building a timber house, feel free to leave a comment and share your thoughts or professional insights with the community. Don't forget to like, share, and subscribe to support the channel, and stay tuned for more real construction projects. Thank you for watching until the end, and we'll see you in the next video.